Right, now with hydrolysis, you can be sure they're going to ask it. They're going to ask it at least for 1 mark, maybe a multiple choice question where it's 2 marks, or they can ask a longer one where it's 3 marks, but I can more or less guarantee at least 1 mark in one of your exams will be hydrolysis. Right, maybe more, I think more. So we always start off with the definition. Hydrolysis is a reaction of a salt with water. So it is when you put something into water. Now, say for instance you start with HCl and you put NaOH there. What will the products be? HCl, NaOH. Products will be sodium chloride and water. Right. Now when we do this, we are adding an acid and a base. Is this acid a weak or a strong acid? Strong acid. Base? Strong. Right. And now if I've got a strong acid and a strong base, they are going to neutralize each other, and what will the pH of the final solution be? That one should be more or less a pH more or less of 7. Right. If it's strong and strong, you will end up with neutral. If the acid is strong but the base is weak, it ends more to the acidic side, and then you will end up. Okay, so you know about that. Now, eventually, if you look at this, you added everything together in a beaker, and what did you get in that beaker? You actually got a salt solution, right? And what is the pH over there? The pH is 7. And now they're going to ask you a question. They're going to say, okay, say for instance, I took water, pure water, and I just added sodium chloride into that water. What will the pH of that solution be? And the answer is also 7. It doesn't matter if I prepared it by adding an acid and a base together to get the salt solution, or if I made it by just adding the salt into water. It doesn't matter. I have a salt solution, and therefore the final product will be like that. Right. So in future, they're going to give you other ones. They're going to say, for instance, if you take ammonium chloride, they're going to ask you, if I put ammonium chloride salt into water, will that be an acidic, a basic, or a neutral solution? And now I have to say, okay, it doesn't matter if I put the salt into water or if I make it by using an acid and a base. So let's go and think, what acid and base should I have used to make ammonium chloride? What acid? Hydrochloric acid. What base? NH3. What do we know about this acid? Strong. What do we know about this base? Weak. So that means the acid is winning. So if I put this into water, it will be an acidic solution. Right. Okay. Go to your books. Let's see how you do this first part. Right in the middle of page 26, you've got this table. Right? And I ask you to give the formulas of the acid and the base that can be used to prepare the salt and indicate if the solution is acidic, basic, and neutral. Right. So you have your compound, and sorry guys, here's a typing error once again. It should not be acidic, it should be what acid must be used, right? What acid must be used, then what base must I use, and what type of solution will I end up with. Now let's talk about the first one, ammonium nitrate. Ammonium nitrate will be NH4NO3. Ammonium plus 1, nitrate minus 1. Okay, so if they ask me that one, which acid should be used to prepare that one? Nitric acid. What do you know about nitric, strong or weak? Strong. Which base should I use to prepare ammonium nitrate? NH3. You can see it inside there, NH3. And what do we know about that one? Weak. So who's winning? Acid. So this will be an acidic solution. Next one, potassium chloride. Acid, hydrochloric acid, which is strong. Base, something that gives me the K, KOH. What do we know? Strong. Strong, strong, neutral. Right, sodium oxalate. Right, oxalate. Which acid should I use? Oxalic. You've learned something today, eh? Yeah. Good. What do you know about oxalic acid? Weak. And that sodium comes from sodium hydroxide, strong. Who's winning? Base. So this will be a basic solution. Right, we get to ammonium carbonate. Now this is difficult because ammonium, if you wanted to write it, ammonium NH4, but you'll have to have 2 of those because they are only +1. And carbonate is -2. So 2 ammonium to 1 carbonate. Okay, so which acid? The one that will give me the carbonate. So it should be carbonic acid. Right, carbonic acid. H2SO4, H2CO3. What do we know about that one? It's weak. It's not one of the 3 strong ones, so obviously it's weak. Hey? And then we get to ammonium. What do you know about ammonia? Weak. Weak, weak? Neutral. Right, sodium sulfate. Okay, but there's something, not sulfate, sulfite. What is sulfite? SO3, not SO4, right? So you have sodium, and you will have 2 sodium to 1 sulfite, because it's 2 minus. Right, which acid? H2SO3, SO3, right? Alite. What do we know about that one? It's not sulfate, so it's not strong, that's weak. And we put that with sodium hydroxide, and sodium hydroxide? Strong. And we end up with a basic solution. Right, we get to lithium carbonate. It's a carbonate once again, so it will be H2CO3 once again. Carbonic acid to give you the carbonate. What do we know about carbonic acid? Weak. Lithium hydroxide? Strong. Who's winning? Base. It's basic. Right. Sodium acetate? Acetate comes from acetic acid. CH3COOH. What do we know? Weak. And sodium hydroxide? Strong. Basic. Okay. But unfortunately, this is only 1 or 2 of the marks. Because once you've done that, they're going to ask you to explain. Okay. You can see it's nearly 1 o'clock. Hey? Right. They're going to ask you to explain by using equations, why is this one making the water basic, acidic, or whatever when it gets into water. Now, I want you to think back. If you think about hydrochloric acid, what do we say about hydrochloric acid? It's strong acid. So if HCl reacts, let me just put that aside. If HCl reacts, you end up with Cl minus and H3O plus. What do you know about HCl? Strong acid. Strong acid. Right. Who's the conjugated paired with that one? Who's conjugated paired with that one? Cl minus. They only have to divide by 1 H plus. Right. So this is the conjugated base. Now, if this acid is very strong, what is the definition of strong? Ionized completely. So every single one is going over to Cl minus. Do you then think the Cl minus will be coming back? No. If this one is a strong acid, then its conjugated base will be very weak. It will not be going back. Something that is strong wants to sit up in the split up form. They don't want to be combined. That's why it is a strong acid. It wants to split up. So if you put chlorine into water, chloride ion, chlorine is what? Cl2, right. Chloride ion into water, it will not be doing anything because it is happy the way that it is. It wants to be split up. Right. So what we're going to do is we're going to say, okay, let's take this example. You've got ammonium chloride. First, just for 1 mark or 2 marks, they're going to ask you, is it acidic or basic? You can say, okay, this comes from ammonia, and this comes from HCl. Weak, strong, acid is strong, it's going to be acidic. There's your mark or 2. Right. And then they're going to ask you to explain. And when you ask you to explain, you're going to take the ions separately. Right. I'm taking the chlorine. What do we know about chlorine? It comes from HCl. What do we know about HCl? It's strong. It wants to be split up. So this one, you just write, it does not hydrolyze. And then you get to the NH4. What will the NH4 form? Where does the NH4 come from? NH3. And what do we know about NH3? It's weak. So a weak one will be going back because its conjugated pair is strong. So if it wants to make something that is strong, it will not react. If it wants to make something that is weak, it will react. And now I want you to turn back just 2 pages to the bottom of page 22. And there I have a table that will help you. If I put a salt into water and it's got a chlorine ion, what will happen to the chlorine ion? Perfect answer, nothing. Right, nothing. Because the Cl minus comes from a strong acid. So this is a very weak base. It will not react. So it will just drift around. So it will not make it basic or acidic. It will just drift around. How about SO4? Where does it come from? SO4 2 minus comes from sulfuric acid. Strong acid. So the SO4 2 minus is very weak. It won't react. So for all of those that come from something strong, they will not react. The same thing for the sodium, potassium, lithium. They will not react. But if you get to these guys, they come from something that is weak. So they are actually strong and they will be going back. So if you get the carbonate atom, where does it come from? Actually from carbonic acid, right? So it will start going back. It will. And now, what is the definition of hydrolysis? Reaction with water. So don't start putting OH minus and H pluses or something strange in there. It's reaction with water. So you take your iron and you take water, and now you know where it's going. If it's CO3, it's actually going to H2CO3, carbonic acid, but just go let it 1 step at a time. So it's taking up 1H, and if it takes up 1H, then that will end up as OH minus. And that would be why that will make a solution basic. Right. NH4 going to NH3. How can it go to NH3? It needs to give off the H+. So that's why the water ends up H3O+, and that's why it will be acidic. So let's just go and do that very last one. On page 26, final one for today. Sodium oxalate. What does sodium oxalate look like? Oxalate, COO, 2 minus, or you can put the sodium in there, 2, right. Sodium oxalate, or you can put the sodium in front. They will take that as correct as well. Right. Dissolved in water. And now they want to know, is it acidic, basic, or neutral? So where does the sodium come from? It comes from sodium hydroxide. And where does the oxalate come from? Oxalic acid. Right, what do you know? The base is strong, the acid is weak. So it's going to end up basic. So for this long question, that would have been worth 1 mark. It's basic. Right, and then they ask you to use equations to explain the answer. Use equations to explain the answer. Now, I'm looking at them separately. I'm looking at my sodium ion in there, and I'm looking at my oxalate ion in there. Right, what do you know about sodium? Where should it go? It can go to NaOH. Will it go to NaOH? No, NaOH is strong, so this one is weak. It will not hydrolyze. Right, so it will not hydrolyze. And then we get to the oxalic one. Now, it's going to react because this comes from a weak something, so it's going back. Weak one, want to stay together. It is hydrolysis, so you have to put in water here. And it is going to COOH2. It wants to go back to the weak state. Right, so you'll have to have 2 water molecules, and what happens when the H is transferred to there? That one ends up as 2OH minus. And this is why it is becoming basic. Because when this oxalate ion comes into the water, it will hydrolyze and it form OH minus, and that will make it basic. So if you find it difficult to write the equations, just turn back and reread that table. Because there I gave you most of the equations that you might need. Right, it's all there.
Right, we're moving on to titrations. Now with titrations, I'm not going to bother with all the calculations. That we're going to do in the next cycle when we're looking at mole calculations. We will also look at this calculation, right? But what I want to look at is, why do we do this? What is the purpose of a titration experiment? And if you look there right at the top, you will see it is to determine the unknown concentration of either an acid or a base. So let's take the example. Say, for instance, you've got sulfuric acid, but you don't know H2SO4, and you don't know the concentration. The concentration is unknown. But what I do know is I know this reacts with NaOH, right, acid and base. Okay, and I have to be able to write the equation. Na, sulfate is 2 minus, so I need 2 of the sodiums, right? And then water is the other product. So acid and base will always give salt and water. And then if I have to balance it, there's 2 sodiums over here, so I need the 2 over here, and then I need a 2 over there as well. Right, so now I know this one. I don't know the concentration, and I want to know what's the concentration. So I'm going to measure it against the sodium hydroxide, right? Now, if we measure something, we put it next to each other. We measure it against something that we call a standard. If I asked you how long this pen is, you would have taken your ruler and said, that is the standard, right? It's measured. Okay. So I can measure it against this. I can see how long it is. And also what's important, this standard of me, it's not made of rubber. It can't stretch and contract, because a centimeter must be a centimeter, right? So what's important is for us, when we have to compare this, we have to compare it with a standard solution, right? And here we have our standard solution. What is a standard solution? It is one where the concentration is known and also it remains constant for a time. You don't want a standard solution that is reacting with the air and going to produce all kinds of weird byproducts, right? Or a different concentration. So you need something that you know the concentration, so it must be known in order to be your standard solution, and it must not react with the air so that the concentration doesn't change, right? It must be known and remain constant, right? So now I have these two, and I'm going to do this reaction. Now to do it, we're going to use 3 types of glassware. So let's look at the glassware first. First, you've got the pipette. Now pipette, it's a glass straw with on one side, it goes to a fine point, and somewhere along the line you have a mark. That is very important, because with a pipette, the most important thing is that it's going to give you a fixed volume. Right? Every pipette is marked. It's something like, I can't even read there, let's say 20 cubed centimeters, right? If it's up to the mark, then you've got a fixed volume of 20 cubed centimeters. Now, how do I do this? Now, if you've got the little mark, you're going to keep it upside and you're going to suck that whatever acid or base until it's higher than the mark. And then you're going to put your finger on top of that straw. Right, you've done that with cold drink lots of times. Right, now the level will stay constant, but if you lift your finger, right, then it will go down a little bit, and you keep doing this until you've got the exact the meniscus, the bottom of the meniscus, exactly with that mark. So when you look at it, you've got a solution. That top layer will make a concave level. We call that the meniscus, right? And you have to measure at the bottom of that meniscus, right? So you need to have your finger on top and let it drop until the bottom of the meniscus is right up to that level mark. Then you've got the correct volume, right? The fixed correct volume in there. And then you're going to take it and put it into what we call the conical flask, right? Now the conical flask is the third piece of glassware that we need. And we also call it an Erlenmeyer flask, right? Now here the shape is very important. Don't go and change it, substitute it with a beaker or something. The shape is very important because when we are putting the acid and the base in there, we're going to swirl it to get a good mix, right? And that shape will give you a nice little sort of tornado down there. You will have good mix, right? And also because you've got this small opening over there, it will prevent spilling, right? So we're going to use the conical flask or the Erlenmeyer flask. So we are going to take that pipette and you're going to take the pipette, the point of the pipette, right up against the glass, right? So right up against the glass. So this is glass to glass, right? It is the glass of the pipette right up to the glass of the Erlenmeyer flask. And this is very important because that is how the pipette is designed to work, right? It is designed not to hold the correct amount, but to deliver the correct amount, right? And you need to press it glass against glass. It was made to work that way. If it's glass against glass, the correct volume will flow out. And then afterwards, if it stopped flowing and you look at the pipette, there will still be a little bit down there, but don't get upset. The guys who designed this knew there was going to be that little bit. They designed it so that it will deliver the correct amount. So if you keep glass against glass until nothing flows out, then the correct amount was delivered. And don't go blowing out that extra drop. It was designed to stay there, right? It always stayed there when they tried it out. Okay. Now, just before I do that, there's a very important thing, and that is what can I use to rinse this pipette? It's been lying on the store shelf for a year since the last time we've used it. What am I going to do? How am I going to clean it? Now, you can do that with distilled water, and remember, not tap water. Tap water might contain ions that will get involved in my reaction. I don't want ions in my reaction that I don't know about. So I'm going to use distilled water, but very important, that's not the last thing I go. The very last thing that you are going to use to rinse it is the solution that will be used in that, right? Because if I've rinsed only with water, I will be left with little droplets of water in there, and then I suck up my solution and it is actually diluted, right? So I don't want water drops in there. So after the water, you rinse it with some of the solution that you are eventually going to use there. Right, so let's go back and see. What have we done already? Now, the first thing is you have to make your standard solution, right? Okay, and we'll talk about the amount, the mass of solute that you need. This we'll look at when we look at mole calculations next. We'll look at that one. But first you have to make your standard solution by taking the correct mass and dissolving it in water. Right. And then the second thing is we are going to put something in there, and we're going to put in the buret, and we're going to put something down there in the conical flask. Right. Now, what's very important, this buret, which is the other piece of glassware that we're going to use, has got a small tap in there, right? It's measured from 0 up there, goes right down, right? Increase as you go along, and then there's this little tap. And what's very important, if you put the base in there, the base, typically in grade 9, you learn the base is soapy, right? Now, if you put the base in there, it might cause a lot of blockage with your tap. And I'll tell you now, the guy who's going to wash this buret will not be happy. So don't go putting the base in there. Please put the acid into your buret, right? But remember, that is for the practical. If you get an exam question, the examiner might give you a question where they put the base in there. It's only on paper, right? So don't assume that they did the right thing, okay? Just check. But when you're doing this in the lab, definitely put the acid in there, then you'll have less blockages and it will go easier. Right, so the second thing is we are going to put the acid in there, but I'm going to put the base in there. So this is my second thing. I'm going to put the base in there. And what am I going to do? I am going to use a pipette. And the reason is I want a specific volume, let's say 20 cube centimeters. You take the pipette from the shelf, that's got the correct volume, right? So here I know both the concentration and the volume, right? And I put it in there into my conical flask, my base, by measuring with the pipette. And that is definitely a fixed volume, right? A specific volume of sodium hydroxide. So the volume is measured and specific and fixed, right? And I put it in there, right? So that was the second thing. The third thing is the indicator, right? I'm going to add an indicator, and that's going to show me when I am at what we call the end point, and that is when there's 2 sodium hydroxide molecules for every 1 sulfuric, when they've reacted completely. Right, now to choose the indicator, down here you've got this table of 3 indicators and you have to learn those 3, right? You have to know. The first one, phenolphthalein, is typically one that is in an acid colorless, but in a base it will be pink, and it changes from colorless to pink around that pH. You don't have to remember the pH, but you have to know that it changes in the basic region, right? Bromothiamyl blue, yellow in an acid, blue in a base, and it changes in the neutral range. And then you've got methyl orange. I always think orange, it's like lemon, it's citrusy. And what do you know about citrus? It is acidic, right? So methyl orange will be the one that changes color in the acidic range, and it is orange in an acid and yellow in a base. Right, so how do I choose this? You look at the acid and the base. If you've got a strong acid and a strong base, very high pH, very low pH, when they've cancelled each other out, they will end up more or less neutral, right? So you've got a very high and a very low pH and you end up neutral, and then you're going to choose bromothiamyl blue, right? Strong acid, weak base, then you're going to end up with the acid winning because that was strong, and you've got an acidic endpoint, and then you're going to use methyl orange. So in this instance, we were working with sodium hydroxide and sulfuric acid, right? What do I know about sodium hydroxide? That is a very strong base, right? And what do I know about sulfuric acid? That is a very strong acid, right? So if you've got strong acid, strong base, you're going to end up with an endpoint that is neutral. And if the endpoint is neutral, then I am going to use, for a neutral endpoint, I'm going to use bromothiamyl blue as my indicator. So I'm going to add an indicator over there. And since it is in the base over there, it is going to be blue. Right, it's going to be blue when I start out. Okay, and then I'm going to add the acid, and then it's going to turn to yellow, or right before it turns to yellow it might be green because we're going from blue to yellow. So right when it changes it will be green. Okay, so now I've got my base, I've got my indicator down here. Next I'm going to add the acid. Now let's talk about the buret. If you talk about the buret, You must read the reading before and after. We don't always go back and fill it up to 0, right? When you start out, you might be at 0, right? If you really paid attention and really wanted to start at 0, but it's not necessary. You can start at 20 and then you just have to read off you're at 24,3 or whatever afterwards. So the important thing is you have to read before and after so that you can extract to see what is the volume that you actually used, right? So what I'm going to do is from my buret, I am going to determine the volume. I'm going to read this, right? Read and subtract, and then I'll have this, right? And that is the whole idea. If I know the concentration, because it's a standard one, and I know the volume, C equals N over V. If I've got C and V, that will tell me how many moles of the sodium hydroxide I will have down in that Erlenmeyer flask. Right, I've put in the base and I know both the concentration and the volume. So I've put it in there and this is the number of moles of base. Right, and now I'm adding the acid, and when it is at the end point, you'll have the color change, and then I'll know for every 2 of those, there will be 1 of those in the beaker. And then I can determine the concentration because then I know N and V, and that will give me concentration, right? So you can do that with 3 steps, or we're going to do that with the 1 equation, but we will look at that when we get to the next cycle, right? So what are we going to do? First thing, we made the standard solution. Next thing, we took the specific volume of the base with the pipette and we put it into our Erlenmeyer flask. Third thing is we added the indicator and then it was all blue, right? Fourth thing is now we are going to add the acid from the buret, right? So you're going to add it drop-wise. Now what is important with the buret is, remember, it's also been standing on the shelf, right? So here we also need to know how to rinse it, right? So you need to rinse it with distilled water, but that must not be the last thing. Same as before. Finally, the last thing you do before you do it, it must be with the solution that you are going to use in that buret. Once again, not with only distilled water. Only distilled water will leave water droplets in there, and then if you add your solution, it will be diluted. So very important, rinse both the pipette and the buret with water, but then with the solution you're going to use in there. Now with the buret, we are now going to put that acid into our Erlenmeyer flask to react here. But if you make it happen too fast, you're going to pass the end point, right? We want to know exactly that moment where it turns from blue to green to go to yellow, because that's where you have the end point, right at the green. So what we're going to do is the first one, we're just going to do a rough one. You don't know, is it going to be 3 cube centimeters or is it going to be 30 cube centimeters that I have to add? So if you go too slow, you will have spent 2 periods dropping 3 cube centimeters and you're not nearly at the end point, and the teacher will tell you, okay, sorry, the time for this is finished. So the first one, we're going to do it fast. You're going to do it quickly, right? And it's just going to give a rough indication of where we have the endpoint. How much do I require, more or less, right? And then you're not going to use that value, right? It's just to give you an idea what to do with the other 3. So then we're going to repeat it 3 times, right? And every time you're going to know, okay, it's more or less at, say, 7 cube centimeters. So I can let 5 cube centimeters go quickly and then start to go very slow, because right at the end point, we add 1 small drop at a time, because we really want to know a very exact volume, right? So that's the last thing we're going to do. We're going to add that until we get the color change, right? And the moment that you get the color change, you're going to measure the final volume and then we can calculate. Right, just one more thing, and that is, how about the Erlenmeyer flask? I've now talked about rinsing the pipette and the buret. I have to rinse them with water and then finally with the solution I'm going to use in them, right? But now how about the buret? About the conical flask. Now the conical flask, you can wash down with distilled water as much as you like, right? Remember, you're actually adding that to both the acid and the base, right? You are not making the moles of acid more or less, right? If you added water into your pipette, or if you rinsed your pipette only with water, you would have changed that concentration, right? If you added water to your buret and not rinsed with the correct solution, you would have changed that concentration. But when you work with the Erlenmeyer flask, you are actually adding it to both, so it doesn't matter. You're just putting extra water in there. You are not changing the concentration of the one or the other. You're changing the concentration of the whole thing, right? And what is very important, if you've got acid, and remember, you are dropping it in and you're swirling this bottom flask. It might happen that you have a little bit of acid that gets left on the side of this. And if it doesn't go in, you will need extra volume from your buret to make this reaction finished. That would already have been the end, but now I have to add an extra because that was not used. And that's a problem. So what we're going to do is we're going to continually wash that down, and we've got a specific wash bottle. You have a bottle, a plastic bottle, and it's got that nice spout that you can use to wash it down. You really need to wash that down with distilled water, because we have to get that. All the things that might be sitting on the side has to go in there so that it can react with each other. Right. So pipette and buret, rinse with water, but finally with the solution that's going in here. This, no other solution, just water, just water, just water, just water, and a lot of water so that you can keep that inside, right? And it will not influence the final answer.